Hello, everyone, and welcome to today's Tech Talk on how hard can it be to commission a heat pump? Experiences with the commissioning of an AHU DX heat pump coil kit. My name is Sherry Adams, and I'll be moderating for today's session. Please note that throughout the Tech Talk, all phone lines will be muted. This will minimize any background noise or feedback that could distract from the presentation. We'll be using the Q&A function. When you have a question, you can submit them through the Q&A function. We will be gathering these questions throughout the Tech Talk, and we'll have time at the end for Q&A. If your question is related to a particular slide, please include the number of the slide in your presentation. A PDF of these slides will be sent to you electronically after this live presentation, and we will be recording the Tech Talk, and it will be available on our website under the resource section. Today's presenter is Stephen Gutman. Steve is a principal of Gutman and Blivett with more than 2 decades of leadership in sustainability and integrated building design for healthcare, higher education, commercial, and civic projects. G&B is a mid-sized consulting engineering firm in California. It is a top recipient of National ASHRAE Technology Awards over the past 10 years and has completed over 85 projects that are LEED certified. Steve has presented on topics concerning sustainable design for the built environment at Greenbuild in 2006, 11, 12, and 18, and at CleanMed in 2006, 8, 10, 11, and 2019. And Steve is also a board member of the California BCA chapter, who the California chapter is sponsoring this webinar this month. So welcome, Steve.
Barry, welcome everybody to talk about how hard can it be to commission a heat pump. Just to get started here, a little bit more about myself and the company. We're in our 65th year of operation. We established our commissioning team about 16 years ago, and I've been running that team since we established it. And as Sherry mentioned, I'm a board member of the California chapter, and I see some other board members on the talk here. So shout out to the California chapter, and we got a lot to cover, so let's get started. So here's the question: how hard can it be to commission a heat pump? You'll tell me at the end of this talk what you think the answer is, but I draw inspiration on this topic from unusual places. So Shakespeare basically said, you know, if you think you know what you're doing, you better think twice. So at least that's in my words. So I think this is really the lesson, and the moral of this story is be careful what you think you know. So the application for this DX coil kit was an existing tenant improvement for a small lab in an existing building. The project had about 7,000 square feet, 5,000 square foot of which was basic medical office space, exam rooms and support spaces, reception, office, et cetera. And then a 2,000 square foot clinical lab, which was really the heart of the project and the area served by the system we're going to talk about. The rest of the space was served by an existing dual duct system with pneumatic controls, which is probably why they decided to abandon that for the lab, because the lab had some very, very special requirements. It's actually an in vitro fertilization clinic. And so high air change rates, a very clean environment, ISO class 8, so HEPA filtration, gaseous filtration, positive pressure control. We only had a high humidity limit, so there was no humidification, only dehumidification. And not that tight a temperature control range, 68 to 74. So the engineer used the existing system for everything except the lab, and added a small air handler to serve the lab. And obviously the key to this air handler was the DX coil and the outdoor air-cooled heat pump condensing unit, which together with a special controller that comes with these kind of systems is what I'm calling the DX coil kit. And we'll talk a little bit more about that. It was originally intended to be a VAV system with tracking pairs. There was no reheat provided in the initial design. which is a red flag for us when doing dehumidification systems and not having reheat. That's just an application that we don't think works very well or at all. So we were able to get the engineer to make some modifications. First, the resettable constant volume. So VAV really didn't work because we needed 15 air changes per hour minimum, and that was far in excess of what was required to meet the cooling and heating load. So VAV was not the right application. This was a constant volume system. We made it resettable so they could go down to reduced air changes after hours, keep the same difference between supply and exhaust, so the pressure relationships didn't change, but just save some energy during the evening hours. Because the constant volume terminal box, the VAV terminal boxes became constant volume terminal boxes, still tracking pairs, and we got the engineer to add reheat. And the way they did it was a little bit unfortunate. They were limited in the electrical infrastructure, so they only added reheat to 4 of the 6 thermal zones, and they left it out of 2 zones. They left it out of the main lab space, and we'll come back to that because that turned out to be kind of a key issue, and that was really the space that would have had the largest reheat coil. And they left it out of one equipment room that had a bunch of freezers in it, so it was really a cooling only space. So that wasn't such a bad decision, and I'll show you the results of that decision at the end of the talk. So that's the application. Now we're going to just do a real quick on what do I mean by a DX coil kit, and maybe you all know, but we'll start as if you don't. So the basic system that DX coil kits were invented to help extend the applications of were VRF systems, variable refrigerant flow systems. So a typical VRF system has a single outdoor condensing unit and multiple indoor fan coil units. And this diagram shows a 2-pipe VRF system. There are some 3-pipe VRF systems. You also have what they call branch selector boxes, which regulate the flow of refrigerant in a VRF system. So that's all left out. Really what's important here is you've got a single condensing unit and multiple indoor units. And the coil kit was designed to be able to add a small air handler with a DX coil and have that operate as part of the VRF system seamlessly. So this system has a smart expansion valve and some controls that interface with the outdoor condensing unit to allow it to operate as an integrated system. And a lot of VRF systems don't handle outside air very well, or a lot of VRF fan coil units don't handle outside air. So really, one of the main applications is putting in dedicated outdoor air systems, combining them with VRF fan coil units, and having a complete system that's refrigerant based and integrated. So we didn't have any of these other fan coil units. We only had a single air handler with a coil and the coil kit and a single outdoor condensing unit. So I've got sort of 3 sections on commissioning challenges. The first section is about factory settings and the challenges of how some of these manuals for equipment that's designed in other countries that are non-native English speakers, sometimes manuals can be written very poorly. So let's get into it. So these DX coil kits tend to have canned programs. So it's like a rooftop package unit where you can define certain parameters of the application, but a lot of the programming is not customizable. It's canned, and so we ran into a lot of issues with these canned programs. Just going through some of the basics, we had to pick whether we were using a third-party controller or the manufacturer's controller. In this case, we had a BMS system that was managing the entire system, so we selected third-party controller. Then we had to select the type of set point control that we used with a third-party controller, and they gave us 2 options. We could use a direct acting over the entire range of available set points. That's type 1, or type 2, where it's reverse acting and cooling and direct acting and heating. So as the voltage goes from 0 to 10 volts in cooling, the set point actually goes from high to low. So 10 volts means more cooling, 0 volts means less cooling, whereas in heating, it would be the opposite. Well, we opted for type 1 control, and we were given a set point range that was available from a low of 1 volt, equaling 46.5 degrees roughly, to 7.4 volts, equaling a little over 82 degrees. And this was not the factory setting in the controller, so that was one of the first things when we started having all these issues. So all of these issues I'm raising here were because the system did not work at all initially, and it's really taken months and months to sort out all of the issues. And we're still fine-tuning some of the things right now. But the first one was, this is not a factory setting, so we had to change dip switches to set it up for third-party control with type 1 control. The next area we had to investigate was what they call capacity control. And so you had two options with capacity control. You had discharge air control, or what they call return air control. And because this is basically a constant volume reheat system, we went with discharge air control. And that happened to be the factory setting, so that got okay. But when you started digging into how the discharge air control was configured, there were two sensors that were key to implementing discharge air control. One they called the discharge air temperature sensor, TH24, and the other they called the return air temperature sensor, TH21. And when you dig into the manual, you find out that the return air sensor is in the duct on the suction return side of the air handler. So, that's a fairly vague statement, on the suction return side of the air handler. So that sounds like the return air. It's called the return air sensor. So that's what everybody understood the sensor was. And we'll talk about why that became important a little later. But that also happened to be the factory setting. So we moved on to the next issue. So when you start to look at how the system regulates heating and cooling, there's algorithms that are pre-programmed where you can change some parameters, but not all of them. And so the return air, having these problems, and we started looking at the return air temperature sensor and realized very quickly that they didn't mean return air temperature sensor. And really the thing that clued us into that was that for cooling, the algorithm said that the return air had to be less than 57.2 degrees to turn off cooling. Well, that doesn't make any sense. If your space is operating at 57.2 degrees, you've got bigger problems. But they clearly did not mean return air when they said return air. So as we talked to the manufacturer, and they frankly were not particularly helpful, it became clear that the return air to us probably meant the entering air on the coil. And so everything else we did subsequent to this, we assumed that we were dealing with a thermistor that was located on the inlet of the cooling coil. And then there were, as I mentioned, there were some parameters that we could actually adjust in the algorithms. Those parameters were only on the heating side, so we could not adjust any of the cooling parameters. But the two parameters in bold here, the one that it basically turns on heating, and the one that turns off heating based on the inlet temperature of the coil, there were ranges of choices that could be made. Now, we didn't know this was important yet, so we just left it at the factory setting, and we'll come back to how that affected our operation, and that was a parameter that did ultimately need to be changed. Time check here. All right. Now, one of the features they provided in their software was an offset for what they called to correct for poor thermistor placement. So, this is probably a bit of a philosophical issue, because if a thermistor is poorly placed, our opinion is the right thing to do is change the placement. Now, in some situations, I suppose you could end up with some limitations on where it could be placed, but rather than using offsets, we adjusted sensor locations. We put some effort into calibrating the thermistors that were used by the canned DX coil kit. We did some calibration effort to align those as best as possible with the sensors that our BMS was monitoring. And we did not use any offsets to correct for poor thermistor placement. So we left that at the factory setting. The next set of challenges I categorize as BMS integration issues. Obviously, if we're using our BMS as the device that decides when cooling is needed, when heating is needed, what the right set point for the supply air is, it monitors filter pressure drop and air handler CFM and all the parameters. All of those controls were put into the BMS. There was a fair level of integration that was needed, and the wiring diagram is supposed to be your resource for connecting external devices to the DX coil kit. And again, when you have wiring diagrams that are poorly documented, use language that's unclear, you can find yourself, in spite of calling the factory and not necessarily getting much help, you can find yourself having to do a lot of experimentation to figure out what the right way to hook things up are. So we did our troubleshooting and we managed to get things hooked up right. So first thing is, the original design called for full BACnet integration between the devices. So we weren't supposed to have two different temperature sensors, one connected to the coil kit, connected to the BMS. Of course, the manufacturer forgot to ship the BACnet gateway with the unit, so that was put on order while the controls contractor was desperately trying to get things working. So instead of waiting, they started hooking up things with hardwired interfaces, and I think they figured that they would get the integration device, and they would integrate some things, and they would have a mixture of hardwired and BACnet integrated, until we found out that configuration was not allowed. So you were either hardwiring it or you were integrating it through BACnet, but you couldn't do both, and that was nowhere in the manuals. Furthermore, we found out that if we were doing BACnet integration, which was the original design, we were going to have limitations. Our lower temperature limit was no longer 46.4. It was now 61 degrees. And we needed a 52-degree set point for dehumidification. So actually, it turned out to be, somewhat of a blessing, if you will, that the BACnet board was missing, because turns out not only didn't we want it, but we actually couldn't go in that direction. Then there were issues with integrating the temperature set point signal. Spanning signals is very common issue. I think that most commissioning agents will run into this issue, and so that's fairly straightforward, and we caught that early and fixed that quickly. But what we didn't catch early was that the terminals for the set point signal were polarity sensitive. So we struggled with that for a while, and then determined that we had a polarity problem. That fixed it. Now our set points were being read by the system. And then here's probably the biggest surprise. With heat pump systems, it's very common to have a reversing valve that is externally controlled. So you tell the system, I want to be in heating. You either energize or de-energize the reversing valve, and it goes into heating. And if you want to go into cooling, you do the opposite, right? So your reversing valve is your control, your mode control. So you put it into heating by controlling or heating and cooling by opening and closing the reversing valve. And that's very conventional with heat pumps. Of course, not this heat pump. So while it was configured for this, an open and closed contact to put it into heating or cooling, it turned out that really the contact that the engineer or the controls contractor used was really an enable contact. It had to be closed all the time that we were running the unit. So when we were opening it to try to get heating and we were not getting any heating, it took us quite a while to figure out that that's not how you put the system into heating. In fact, way this system went into heating was by it made its own decision. You gave it a set point. It checked the discharge air conditions and the entering air conditions at the coil and decided whether it needed to be in heating or cooling. So you really had no direct control over whether the system was in heating or cooling other than giving it a set point and assuming that the system would do what it needed to meet that set point. The final set of challenges really came in when we were trying to coordinate but the BMS system was assuming a sequence of operation or a sequence of operation that were implemented and controlled by the BMS related to things like mixed air temperature and room temperature and how these factory controls worked. So the engineer's design had a separate loop for mixed air control. So there was a set of economizer dampers, a mixed air temperature sensor, and a set point, and the dampers mixed return air and outside air to try to meet a mixed air temperature set point. Fairly conventional until we realized that our mixed air temperature control set point was 60 degrees. We had very high air changes, so we really didn't need 55-degree air as a minimum design temperature, even though the system was designed to be at 55. The mixed air was set at 60 degrees. And the factory controls would not let the heating come on with a 60-degree air temperature. Again, this is one of those algorithms where until the entering air is below 57.2, your heating was not allowed to come on. So here we are, giving it an 80-degree set point. The entering air temperature is, 59.8, and we can't get 80 degrees off of this unit. And that sent us, spinning around for a while. Until we finally basically decided to change from the factory setting to a higher temperature thresholds for enable and disable or enable and disable for turning on and off heating. And that pretty much solved the problem. And so we were getting heating when we started giving it the set points that put it into heating mode. And finally, we had because of this original choice of not putting a reheat coil in the main lab, really what we had was a single zone air handler. So we couldn't give it 55 degrees to the main lab 24/7 and let the zones reheat because there was no reheat in the main lab. So the temperature delivered to the main lab had to fluctuate based on the load in the lab. And so the main lab became the master zone, if you will, that determined what the supply air temperature of the whole system would be. And all the other zones were expected to reheat, except for the one zone that didn't have reheat, the equipment room, was just going to get whatever air temperature it got. Not the greatest design, but it turns out it seems to be working reasonably well in this application. Part of what drives that is that the main lab has a lot of equipment in it, centrifuges, incubators, microscopes, and so it does have a fairly high cooling load compared to the other spaces. And so it does tend to drive the need for, the lower air temperatures on the other labs or the other zones. Now, the engineer initially specified a sequence of operation with a constant cooling design air temperature, a constant heating air temperature, a constant dehumidification air temperature, and a statement that said the supply air temperature should be reset based on the greatest heating demand. Never quite figured out what the engineer was looking for there, but we couldn't deliver constant temperatures because of this master-slave situation with the main lab. So we convinced the engineer to change it to basically master zone control of supply air temperature. So the team decided to do a trim and respond control of the supply air temperature based on the master zone set point, and then the actual temperature offset from set point. And then we realized that when we went into dehumidification, where we were supplying 52-degree air consistently in order to dry out the air. That's in our climate, 52 degrees gets you pretty decent dehumidification, and we didn't have a lot of humidity load. But once we went to 52-degree air, we started overcooling the main lab because it didn't have any reheat. So we really wanted to minimize periods of dehumidification. So we added some controls to limit the amount of outside air if the outside air was more had higher moisture content than the room air at the highest humidity limit and the current temperature set point. So that really drastically reduced the amount of time we spent in dehumidification, and has pretty much, at least during the last few months, we've been able to control high humidity by just controlling the economizer dampers. We haven't had to go into dehumidification at all. So this is what actually happened. I'm getting down to the last few slides here, so I think we're on time, right, Sherry? Yeah, may even end a little early. Hopefully I didn't talk too fast for people. So as recently as March 15th of this year, we were still dealing with temperature control problems. This is the green is the room temperature, the blue and red are the cooling and heating set point limits. And as you can see, the room temperature is not staying within our design criteria. It was falling outside, getting cold for long periods of time. And when you add in what's happening with supply air temperature, you can see that, and I know this is complicated to read here, but the yellow line, if you can see that, is the temperature set point, and the black is the actual supply air temperature. Our supply air temperature was not following the set point very well at all. I mean, we were requiring about an 80-degree supply air set point at a time where we were delivering 66-degree air. So, the supply air temperature and the set point control and the set point were really struggling to meet up. And this became quite a bit of discussion with the manufacturer, and they felt our trim and respond was too aggressive, so we changed our trim and respond values to be less aggressive, and that definitely had a positive impact. And so here, as recently as June 3rd, still a bit of migration outside of our temperature control band, but much less, much more stable temperatures. And you can see that the supply air temperature in black is definitely following the set point a little better, but it has these excursions every once in a while. And that's something the manufacturer is still working on to try to help figure out, why, after 30 minutes, the thing sort of goes haywire and set point. So the actual temperature deviates so far from set point. But in general, our system is staying in our, I think I said 68 degrees to 74 was our design criteria, and we're generally 69 to 73. So it's not a pretty picture, and really what it turns out is that DX systems are really not well suited for tight temperature control. You use DX rooftop package units in very conventional VAV reheat systems. And so if your supply air temperature gets a little over cold for a short period of time, you're usually not switching it between heating and cooling. Usually heating is at the terminal end. And so DX systems are really well adapted to that. They're not well adapted to this kind of single zone control with tight temperature requirements. And so in hindsight, I'm not sure we had much choice. We didn't have any heating hot water in the building. It would have been very expensive to put in heating hot water for 2,000 square feet of, and chilled water for that matter, for 2,000 square feet of lab. Perhaps a different DX system without this coil kit might have been more flexible. But of course, we had such custom requirements with the filtration. We had 3 sets of filters in the air handler and fan filter units in the ceiling of the main lab to get down to ISO 8. this is probably, was probably the right application. And at the end of the day, thankfully we gotten to the end result. And that's what I had prepared.
Thank you, Steve. It looks like we have some questions that have come in. So the first one here is, how did reduction of outside airflow not cause the ventilation to be inadequate?
So we had a minimum outside air requirement of 5 air changes per hour. So when we help the engineer come up with what the setback should be during the unoccupied mode, we made sure that we still had 5 air changes per hour of outside air. Which is far in excess of code required, ventilation. I mean, code required ventilation for the space was, less than 1 air changes of outside air. So we had plenty of ventilation there. That's if I understood the question correctly.
Okay, great. The next question is, it seems like as the commissioning provider, you were more involved than you should have needed to be in system configuration. Was your involvement consistent with what services you were hired to provide?
So it's a very interesting question. So this client happened to be Kaiser Permanente, and this may be familiar to people who are, California-based commissioning agents, but Kaiser's expectations of commissioning agents is far beyond what most clients expect. And in fact, now under the current requirements from Kaiser, commissioning agents are required to stamp the control drawings. We're required to write the sequences of operation. So Kaiser has very high expectations of the commissioning agents to be an integral part of the design team to ensure that systems work. That said, I will say that, in general, what clients want is a system that works. And as commissioning agents, if our expertise can ensure that systems function properly at the end of the day, then I think, in my opinion, that is our obligation, right? And so if we see something that won't work, we have an obligation to say so. Now, the engineer in this situation made all the decisions. We did not tell the engineer, you have to do this. We basically made recommendations. We explained why we thought our recommendations were, reasonable and appropriate. At the end of the day, the engineer of record, had to make the decision. And that's how we sort of preserved the separation of powers, if you will, between the commissioning provider as not the designer. That said, Kaiser continues to blur those lines as they get us more and more involved in design.
Great. And let's see, it looks like we have some wonderful comments that have been coming through, which is great. It looks like there might be another question here at the bottom. And what was the MAP coordinator doing on your project?
I will say we had a very engaged MEP coordinator who, we leaned very heavily on to mobilize people and, get contractors to take action. That said, this was far outside our MEP coordinator skill set in terms of troubleshooting these kind of issues. It was a very aggressive project schedule, which was set back a bit by the pandemic. But construction in California, I think we stopped construction for maybe a month, and then construction was resumed under pandemic guidelines. And at the end of the day, I think the project came in a few months behind schedule, but only because of the indoor air quality requirements, not because of the temperature control requirements. We had some real issues with high levels of some aldehydes, which ended up having to do multiple tests and chase aldehyde issues for a few months. But yeah, the MEP coordinator, again, got what we needed out of them, which was the ability to get people at meetings and to, get people action. But the troubleshooting side of things was not going to happen on their watch.
Okay, and then it looks like we just got one more that just came in. Do specifications require or MEP contractor, general contractor, purchase factory, manufacturer startup? And is there expertise locally to support this equipment versus the tech phone line or trial and error you described?
Yeah, really good question. There was not a requirement for factory startup. There was a requirement for a trained technician to do startup, but you see this a lot where contractors believe they have all the training that's necessary to start up a heat pump system or any refrigeration system. When things got, a little out of whack, we did reach out, or the contractor reached out to the manufacturer, and we actually got really what I was told was extremely high level support from a factory trained technician, and even he was baffled initially by many of the things we saw, and he's the one who started calling the factory to try to figure out what was really going on. And as we got deeper into it, what we realized is I think at the end of the day, this is maybe a fairly new product for this manufacturer, and so we were kind of getting the beta version of the software. They even, I think, did a firmware upgrade. We've been given a new manual that doesn't refer to a return air sensor anymore, but now it refers to an outside air sensor, which I think is equally as confusing. And so I'm not sure this manufacturer really had this product ready for market. This is really maybe where we end up. But yeah, I think it's a really good point that factory startup, and especially with refrigeration systems, thorough, well-documented startup of refrigeration systems is something, as a commissioning agent, you really want to make sure happens. And I have to say, we often have to fight for that.
Okay. Okay. Well, so we got a few more that came in, so we'll try to get to a few of them. And if we don't get to all of them, I'll be sure to make sure Steve has the questions to get your answers to you offline. But let me just do a couple more here. How many issues? I think how many issues did you have in total, and how long did it take to get them resolved?
Oh, geez. Well, of course, we our services started in the design phase. So, we had I think 100 design phase issues, and I think we had over 100 construction phase issues. So it was a challenging project. There were a lot of issues, some of which, in all fairness to the contractor, were base building issues that were referred to the landlord, and it's taken an inordinate. I mean, this project was occupied in October last year, and I showed you a March trend log that still showed, fairly questionable temperature control. So, November, December, January, February, that's 5 months after occupancy. We were still chasing temperature control issues. We're kind of over the worst of that. And so the June one I showed you, 8 months after occupancy, is much better, but there are still issues that, we have a long ongoing relationship with Kaiser. And so, we put in a bit of extra effort to make sure our projects are successful with them. And so we're still trying to get the manufacturer to fine tune the tracking of supplier temperature and set point. But yeah, it was a complicated little project for such a small space.
And is there something you would do differently during the design phase? And if so, what would it be to make the process go faster, or job faster?
Yeah, I think that two things come to mind. One is I probably would have advocated harder hindsight for putting a reheat coil in the main lab, regardless of the impacts. And because Kaiser and their expectations of commissioning agents, are such, and the way they measure performance, which I won't get into, that Kaiser's been doing a lot of seminars, and so hopefully if anybody's interested, you'll have a chance to hear about Kaiser's approach. But you know, I probably would have advocated more for what we believe would have been a more robust design solution. And then knowing what we know now about these DX coil kits, if we ever had, or any packaged, frankly, packaged factory DX system, during the design phase, we put a lot more investigation into an application. You know, we do a lot of rooftop package equipment, but fairly conventional applications. And so we think we know, you know, how these systems respond. But when you get into an application like this with tight temperature and humidity control, we'd probably put a lot more effort into looking into how the factory controls really operate to make sure that the design intent is compatible with the factory controls.
Okay, and let me see if I could do one or two more. Were there issues with firmware versioning or the IOM's technical bulletins not matching the firmware version?
Yes.
Okay.
That's a simple answer.
Okay, I didn't know if you were going to expand on that, but I didn't want to interrupt you. Okay. This other question, does the pipe design, or can the pipe design have a big impact on the DX operation?
Yeah, there are definitely issues related to length of piping, both installed length and effective length, you know, adding in elbows and other fittings. As far as we could tell, everything was within the manufacturer's guidelines. You know, they actually just put a factory monitoring tool this month on the unit to gather their factory data that they need to really understand what's going on the refrigeration side. So we're hoping to get a report any day about what they discovered, and if they discovered anything like excessive pressure drop between the outdoor unit and the indoor unit. But at the moment, that doesn't seem to be a problem. But certainly there's maximum elevation differences between condensing units and evaporators. There's maximum pipe lengths, or maximum pressure drop, I should say, which can be affected by pipe diameter and length. So definitely something worth paying attention to. Manufacturers generally do a good job of giving you guidelines, and so as a commissioning agent, you know, you don't have to get too involved in the design other than making sure you stay within the manufacturer's guidelines.
Great, thank you. And I think there's just one last question. We'll just wrap it up here. Then the end result is between, I think you were talking about this earlier, the end result is between 69 to 73 Fahrenheit or F. Do you think it will be acceptable for a hydronic system to get this result? And
so I could take this question two ways. Could a hydronic system keep it between 69 and 73? And I don't think that's what you're asking. Of course, the answer would be yes. I mean, a hydronic system generally can achieve tighter temperature control than a DX. And the DX system, this is actually, I think, pretty good control for a DX system. And of course, we were given 68 to 74 as the acceptable range. Being a lab, experience is they generally like it a little on the cooler side because they're gowned up, and you know, so they like it to be a little on the cooler side. So I think for our project, everybody considered this a success. But if you're trying to do a very, you know, we do some labs that have, you know, 70 degrees plus or minus 1 degree. I would not try to do that with a DX coil kit. You won't achieve it. So there are definitely labs where tighter temperature control would be an expectation.
Great. Well, thank you, Steve. We really appreciate all your time and expertise today. Thank you, everyone, for all your questions as well. Also, just one quick note, if you haven't already done so, please fill out the members survey that was emailed out last week and I believe the week before. We would really value your feedback and want to hear from you. So on behalf of the BCA, thank you, everyone, for your participation and have a great day.